Hello. In this video, we're going to review the theory of capacitors. Our objectives are to look at the definitions, key terms, theory of operations, capacitors in series and parallel, DC circuits, AC circuits, capacitive reactance, and power. All right, the first thing is the definition. Capacitance is the ability of an electric circuit or component to store electrical energy by the means of an electrostatic field. A capacitor has the ability to store electrons and release them at a later time. Here's a couple examples of capacitors. So the first thing when we look at our terms, we have capacitance. That's the ability to store energy in an electric field. So if something has capacitance, it can store energy in an electric field. Sometimes we'll show an electric field like this. This is a vector symbol. And when we have a capacitor, or any time that we have something that stores charge, you can think of like a lightning from a rain cloud or something like that. An electric field is, this is the symbol for a capacitor, but electric field is what happens when we have a difference in voltage between two metal conductors, and the energy that's stored there is an electric field. So if you think about like if you were in a library and you're walking around and then you see a door, so this is my door, and then you have a doorknob, and let's say that you have carpet inside that library and you want to walk around and you rub your shoes on the floor, and then right before you go and touch that doorknob, there's going to be a charge difference, a voltage difference between you and the doorknob, and as soon as your finger gets really close to the doorknob, you'll see a little arc between the ground, which would be the you, and the doorknob, and that's going to create a little bit of a spark. That energy that's available is stored in electric field when you become kind of charged up from walking around in the library. A capacitor is a device that's designed to store energy effectively. So this would be like our electronic devices that are designed to use the electric fields and store energy. So this is our component. So this is our actual device. The farad is the unit of capacitance. So just like when we have a resistor, it'll have a certain resistance. When we have a capacitor, it's going to have a set capacitance. Most of the time, the capacitance that we'll be dealing with will be in the microfarads range. So that's micro 10 to the negative 6 range for most of the capacitors that we'll be dealing with. Capacitive reactance, just like for inductors, there's going to be a X sub C, so this would be capacitive reactance. We remember X is for reactance, so we can have reactance in inductors, or we can have reactance in capacitors, and that's equal to 1 over 2 pi F C. So this is in inversion. If we remember from last time, inductive reactance was 2 pi FL. The capacitive reactance is 1 over 2 pi FC. So what's going to happen is when we get larger capacitors, we're going to get smaller capacitive reactance. Capacitive reactance is measured in ohms, and that's how we're going to solve for voltage and currents in AC circuits. All right, so let's look at the theory of operation. Last time we did this with inductors. This time we'll do with capacitors. So let's say that we have a simple circuit. So here is a DC supply, and let's say that it's 1 volt. And then we have a switch, and then we have a resistor. And what we're going to do is we're going to close the switch. And this is a resistor, let's say it's 1 ohm. What will happen is as soon as we close the switch, so let's say we close the switch at this point here, and we looked at voltage versus time, what we'll see for a resistor is that as soon as we close the switch, our voltage would go right up to 1 volt. And then if we open the switch, it would go back down to 0 immediately. If we looked at current, we would see the same thing. If we looked at current versus time, as soon as we close the switch, the current would go up to its maximum. It would stay, in this case we have 1 volt and 1 ohm, so this would be 1 amp, and it would stay the same. Now, if we have a capacitor, so let's say that we do the same circuit, but we're going to swap out the resistor for the capacitor. And let's say that we have 1 volt and we're closing the switch. And we're going to call this C. We don't really care about the value here. What's going to happen is a capacitor in this circuit is going to oppose a change in voltage. Now, if we remember, when we had inductors, they oppose a change in current. Capacitors will oppose a change in voltage. So when the voltage is changing, the capacitor is going to provide opposition. So what's going to happen here is if we looked at the switch turning on and we do the voltage across the capacitor, so this would be VC, it's going to start at 0. We're assuming that the capacitor is discharged, and it's going to charge up to 1 volt. As soon as it gets charged up to 1 volt, what's going to happen is the current is going to stop. So if we looked at the current going through the capacitor, the current is going to, as soon as we close the switch, the current is going to go to its maximum. So this would be the 1 amp here, or actually not 1 amp, whatever the current is. The current would be dependent on the resistance in the circuit, and we don't have resistance here, so let's just ignore that. What's going to happen is the current's going to go up, and then it's going to go down here, and as soon as we get to our 1 volt, the current is going to equal 0. This is going to be an exponential function of increase and decrease. And so what's going to happen in the circuit is if we connect it to 1 volt and we close the switch, basically the capacitor will be charged up to 1 volt. Then if we open the switch, and let's say we took that capacitor and moved it out of the circuit, what's going to happen is we would still measure the 1 volt across here. So the capacitor will stay charged. So the capacitor is going to store energy, and if you touch a capacitor, this is one of those safety things, you want to be careful because this will store energy for a very long time. If you had one of those big TVs that were built back in the 80s and 90s before there was LCD screens, they had capacitors in there, and you'd always see warnings if you took the plastic covers off that the capacitors are not will not discharge just because you removed the power. The only way to discharge a capacitor is to make a connection between the positive lead and the negative lead. So what you need to do is you need to be able to let these electrons that are stored on this negative plate get back to the positive side to discharge. Now you can discharge them by putting a resistor across here. So how long this takes to discharge the capacitor will be related to the resistance times the capacitance. And in the lab, sometimes what we do is we'll charge up the capacitor and then we'll put our voltmeter across the capacitor. A voltmeter has approximately 10 mega ohms of resistance, and you can actually see the voltage on the capacitor discharge on the multimeter. All right, so how do we make a capacitor? The capacitors that are kind of made by this, that are in kind of this cylindrical shape, are made by taking a metal foil or plates and placing them near each other and separating by an insulating material, such as air, paper, mica, oil. This is called the dielectric. So what we have here is we have to make a capacitor. We take a conductor, and here I'm showing it as kind of like a metal plate. Then we take another metal plate, and then we separate them a certain distance, and then in between the plates, we're going to put an insulator. So it looks kind of like a hamburger, where the buns are metal conductors, and then there's a kind of where the meat would be is the dielectric material. So this would be the dielectric. And what's going to happen is we have all these, in a conductor, we have all these electrons that are easy to move on both sides of the plate. And when we charge up the capacitor, what we're going to do is take the electrons from one side. So if I have a so this is one of my plates, and here is another one of the plates, and I have these negative charges. If I connect it to, let's say, a DC supply, what's going to happen is this is going to operate like the pump, and I would take these charges from this side and I would store them on the other side. And so these charges would kind of come over here, and what you'd end up with is a difference in charge, which would be a difference in voltage across the two plates. And so once these electrons are taken from one plate and stored on the other, we get a difference in voltage, and we can store energy, and then between these two we would have this electric field, which would be determined based on the amount of charge that we could store between the plates and how close the plates were together. Factors for capacitance. So the first thing that we would look at is the area of the plates. Basically, if we have more surface area, we would get a higher capacitance value. The idea is more surface area, you'd get, so if I increase the area, I would get an increase in the number of electrons that I could move. So that's going to determine how much capacitance that I would have. The type of dielectric is very important. This is one of the key factors. The material between the two plates, better dielectrics, better capacitor. And then the next thing is the spacing between the plates. If you can get the plates as close as possible, you can also increase the capacitance. All right, so let's look at what happens if we have capacitors in series and parallel. So let's say that we have capacitors in series. So here we'll draw a couple of capacitors. This is the symbol that I use most of the time for capacitors. So I have C1, C2, and C3. When we have capacitors in series, they're going to add like resistors in parallel. So the total capacitance is going to be C1 to the negative 1 plus C2 to the negative 1 plus C3 to the negative 1, all to the negative 1 power. So capacitors in series are going to add like resistors in parallel. And the idea here is, let's say that we have some different capacitors. Let's say that this one is 1 farad. That would be a huge capacitor, so I'm going to draw it very big. And then this capacitor here, let's say that this one is a little capacitor. And then we have medium-sized capacitors. So let's say that this one is like 1 microfarad. What's going to happen is, if we think about how the electrons are going to work, we have a bunch of electrons on this big capacitor, but we only have a few electrons on the little capacitor. And so, and let's say this one's just a medium capacitor. So the limit to how much, in order to store capacitance, we need to get these electrons from one side of the plate to the other. This capacitor right here is going to limit, it's going to be the limiting factor because it doesn't have enough electrons to store on these plates. In between the capacitors, this area here is an insulator, so there's no way to get the electrons from this plate to the other plate without going through the battery back around. So we're assuming that we have a battery here. Let's draw that on there. And so we got to get these through, and what's going to happen is when we get to this little plate, that one's going to limit the capacitance. So we're going to get less capacitance when we add capacitors in series. In practice, it's not common at all to add capacitors in series. It's not something that we would typically do. It's not a practical circuit. What about parallel? Well, if we think about capacitors in parallel, so let's say that we have a supply here, and we have let's say that this is a little capacitor, and then we have next to it a big capacitor, then we have a medium capacitor here. Putting the capacitors in series, you can kind of visualize it. It's kind of like making the plates much larger. So capacitors in parallel are going to add together. So C1 plus C2 plus C3. So this would be C1, C2, and then C3. So what happens here is when we have these capacitors, if we keep adding them in parallel, we get more capacitance. DC circuit, so let's look at what happens in a DC circuit. If you look here we have a resistor and a capacitor. So this is what we would sometimes refer to as an RC circuit. And when we close the switch, what happens is we're going to get a ramp, and this is kind of what we talked about earlier. We're going to get a ramp of the voltage across the capacitor. This is trying to show the voltage across the capacitor here. That's what these ramps are showing. And how big this resistor is will determine whether we charge fast or we charge slow. So if R is big, so we'd have a lot of resistor, let's say in this case it's 10K ohms, so that's a pretty high resistance. That means that this is going to limit our current, so we would charge slow. If R is small, so let's say that it's 10 ohms, then it would charge fast. And depending on the value of R and C, that will determine the time constant, tau, which is R times C. This is called the time constant. We're not going to deal with that too much in this class. It's R times C. So if the combination of these two is large, it'll charge faster. If the combination of these two is small, it'll charge. I'm sorry, I think I said that wrong. If the combination of R times C is big, that means that we would charge slow. If the combination of R times C is small, we would charge fast. It's a little bit confusing. It's an inverse relationship. The idea is if the resistance is higher, it will limit the current. And so when the resistance is large, we'd get a big tau, we'd have a slow charging. It would take a long time for the capacitor to charge up. Here's an example showing some more of the math behind the circuit. We're not going to do these math problems in this class. Here we have a 100 volt supply. We have a 0.5 mega ohm resistor, so that would be 500K, and then we have a 10 microfarad capacitor. So here they calculated the time constant as 5 seconds. When we deal with these circuits, again, we're not going to worry about them in this case, but it takes 5 time constants in order for the capacitor to become fully charged. So this would be 1 time constant, which would be 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. So what we're looking at is this amount of time and how far we're charged. So this would be 5 tau, so that with tau being 5, this would be 25 seconds. So if we hook this up, it would take 25 seconds for the capacitor. The red line here is the voltage across the capacitor. The kind of purple line here, this would be the voltage across the resistor. And so what we're going to see is that as soon as we close the switch, so we go to charge, the voltage across the resistor would be 100 volts. And then we'd get our maximum current. 100 volts across the resistor, the current flowing in this circuit, I, is going to equal the voltage across the resistor divided by the resistance. So we get the maximum current right at the beginning. And then it's going to start to slow down. The current will start to slow down, and our rate of charging the voltage will also slow down. If we connected the circuit and went to discharge, what would happen is the voltage across the capacitor would equal the voltage across the resistor, and we would see it discharge. So if we were on discharge, what we would see is as soon as we hit the switch, we would be at, let's say we're at 100 volts. As soon as we hit the switch, we would get a graph that looks like this. It basically would be equivalent to this graph. They would look exactly the same. And it would take 25 seconds for the, this would be 0, and it would take 25 seconds for the capacitor to discharge once we put it on discharge. We're not going to deal with these too much for this class, but there are math formulas that we could figure out how long does it take to get to a certain voltage across the capacitor. Capacitive reactance. So when we have, so here we're showing a AC circuit, and we have a capacitor, and the amount of AC current that flows is going to be related to the capacitive reactance. So the opposition to the flow of AC current offered by a capacitor is called the capacitive reactance. In this case, they're showing X sub C equals 60 ohms. So this would already be calculated. And then we can use our Ohm's law formula. Voltage equals the current times XC. So when we have voltage, our Ohm's, when we have a AC capacitive circuit, the current is going to be related to the voltage supplied and the capacitive reactance. That's what they're using here, is this formula off of the Ohm's law. So when we have our Ohm's law, if it's a purely capacitive circuit, we can replace the R's with X sub C. Capacitive reactance is measured in ohms, just like resistance and inductive reactance. So if you remember, we had X sub L last time, and X sub C is how we're going to calculate this for capacitors. If we have a larger capacitor, so the larger the capacitance of the capacitor, the lower its capacitive reactance or opposition to AC will be. The formula for capacitive reactance, X sub C, is 1 over 2 pi FC. So what's going to happen is as we increase the capacitance, we'll get a decrease in the capacitive reactance. Same thing if we increase the frequency, the capacitive reactance will go down. So if we look here, when this is bigger, if it's in series with the light is brighter. If the capacitance is less, the light would be dimmer. So it's an inverse proportion. So when C goes up, XC goes down, and when C increases, XC goes up. Here's our formula again for capacitive reactance. The capacitive reactance XC is 1 over 2 pi FC. F is the frequency, C is the capacitance, and this will give us in ohms. So if we had a circuit, let's say, and we had 2 capacitors, we could figure out what and the capacitance is known, we could figure out what X sub C is for each capacitor, and then we could figure out what the current is. So we'll follow the same kind of process with inductors with capacitive reactance. One other thing to note is that when we have capacitive reactance in series, so let's say that we have a series circuit, the capacitive reactance total is going to add like resistors. Because it's in ohms, this is going to equal X sub C1 plus X sub C2 in this case, and however many we had. If we had capacitive reactance in parallel, our X sub C total is going to equal X sub C1 to the negative 1 plus X C2 to the negative 1, all to the negative 1. So this is going to be different than capacitance. When we had capacitance, our C total was C1 plus C2. And in series, our C total was C1 to the negative 1 plus C2 to the negative 1. So one of the things to kind of note here is that when we have series and parallel circuits with capacitive reactance, it's in ohms, it's like resistance. When we have capacitance by itself, it's the opposite. It's the other formula that we have to use for series and parallel. Here's an example. So we have a 100 microfarad capacitor and it's connected to a 120 volt 60 hertz source. So the first step is determine the capacitive reactance of the capacitor. So here they're showing it down here. Our formula, X sub C is equal to 1 divided by 2 pi FC. So I have to do that in our calculator. On my calculator, I'll usually do this way. So I'd say 2 times 3.14 times 60 times 100, and then you'd have to do the EE negative 6, and then I would close the parenthesis and then do to the negative 1. And if you do that, you get 25.6 ohms. And then the next part, it says what's the current? They're going to use this formula. Current equals voltage divided by X sub C. So we take 120 volts divided by 26.5, and we would get 4.53 amps. When we have a circuit like this, so we have a capacitor in a AC circuit, what's going to happen is we're going to get a phase shift. So the voltage and the current are not going to be in phase. And the mnemonic that we always use for these is Eli, the Iceman, I guess, is one of them that we use a lot. So voltage and inductance, the voltage leads the current. In capacitance, the current leads the voltage. So what's going to happen is the current gets to its peak first when the voltage is 0, and it's going to start to go down. And so if we kind of continued this out here, what we would see is that the current is always going to get to its peak first before the voltage does. So it's kind of a inversion of inductance. And so what happens is these two, if we get if we have a purely inductive circuit, we'd get a 90-degree phase shift. If we added some resistors in here, that would actually cause this waveform to move to the right a little bit. If we added inductance, it would also move to the right. The maximum value of the current score corresponds to the time when the capacitor is fully charged and has 0 volts across it. So we get the maximum current when the voltage across the or when the capacitor is fully charged. For power, capacitors, just like inductors, do not dissipate any energy. It only stores energy temporarily. So when we have capacitors, the unit that we would use for the power, so if I said the power for a capacitor, that's going to equal, in this case, they're showing 0 watts, but let's say that we had like 100 or something like that. We would call this VARs. So in this circuit, we have 240 volts and 5 amps. So the power of the capacitor would be, if we multiply those two together. So let's do that. So I'm pulling up my calculator. 240 volts times 5, and you get 1.2 K bars. So this one here, I probably should just take this one out of here. The power for the capacitor is in volt amp reactive. There's no true power or watts with a capacitor because just like the inductor, it's going to put energy into the circuit and then take energy out of the circuit and then take energy out of the circuit and then put energy into the circuit, and the net effect is going to be 0 watts. Now there's still both voltage and current present, and so there's still a power, but it's not a true power, it's the reactive power, which in this case would be 1.2 K bars. All right, that's the end of this video. Thanks.